Alright, this is a Unit 4 review for ENGR 201 final exam. So in this problem, this is kind of a continuation from Unit 3, but we're going to apply this magic called Lagrange multipliers, which is essentially just following this equation. Del F equals lambda del G. There's a reason why this works. I don't get it. I just know how to do it, so I'm going to show you how to do it. So first, del, remember del is equal to partial with respect to x I plus the partial with respect to yj plus the partial with respect to zk. So I'm going to do this for both f and g. So the first one is going to become, so my equation is going to become, I'll write this in green, 2xi plus 2yj. There's nothing for z, so it's 0k. This is going to equal lambda times, now this is a function of f, this is a function of g, which is of x and y equal to 16, which makes this your function of g. And take the partial of that with respect to x is going to be y squared I plus 2xyj. So now we're going to go ahead and make two equations for this. The two equations are going to be from your I and from your j. And remember, we need three equations because we have three unknowns, x, y, and lambda. So we need a third equation, which is just going to be that x y squared equals to 16. So our I equation is going to be everything with our I terms in it. So right here and here. And then our j equation is going to be all of our j terms with it. So now our I equation is going to become 2x equal to lambda y squared. And our j equation is going to become 2y equal to our 2xy lambda. So now you need to find a way to get your points out. So if there's going to be multiple lambdas, note that there's going to be a lot of points to check. But since it says find the minimum value of f of x, y, I'm probably only going to get 1 point out of this, because normally they'll say if there's more than 1 point, they'll say find the max and min. But look at the wording of your question. So this is find the minimum. So there's probably going to be one value to check, because if you have more than one value, one of them is going to be a local max, or one's going to be a local min, or a max value or a min value. So the strategy I normally employ is to just find ways to cancel out stuff. Like in this case right here, this j equation, I know that I can cancel out 2y. So now I have 1 equals lambda x. And then I'll go ahead and solve for lambda. That equals 1 over x. Or actually, I'll go ahead and solve for x. And that equals 1 over lambda. Actually, this is just bad. I'm not going to do this. We're going to have, let's see. We have 1 equals lambda x. Let's see here. I'm going to do, so the normal strategy I try to do is cancel out lambdas. So I would do, I'll do the I equation over the j equation. So I would do 2x over 1 equals lambda y squared over lambda x, which then we're going to get 2x squared equals y squared. So now I have a y squared. So again, because what happened is my lambda's canceled. I move this x to the other side. So now I have y squared equals 2x squared. So I can plug this 2x squared in for this y squared right here. So then that would imply 2x cubed equals 16. I can divide by 2, so I have x cubed equals 8, which then implies x equals 2. And then if x equals 2, that implies y equals 8, because you're going to square it and then multiply by 2. Actually, y squared equals that. So y equals the square root of 2 times 2 squared, which is the square root of 8. And then that means our minimum value is going to be f of 2 comma square root of 8, which then equals 2 squared plus square root of 8 squared, which then equals 4 plus 8, 12. So a normal strategy I employ is find a way to cancel out the lambdas by making a ratio of the left side, the left side of the equation and the right side of the equation, so I over j, cancel out those lambdas, and then try to make an equation with your x and y. If you do have 3 variables, by the way, so if you have x, y, and z, it's a possibility. I suggest trying solving for lambda, solving everything in terms of lambda, and plugging it all into your constraint equation. But that's the best advice I can get. Alright, so now this is the part. I hope everyone is past this. When I got to this point on the for the final, when I took it, I had a better understanding. I wasn't as afraid. I know the first time this was really hard, but this time it should be pretty straightforward, or at least more understandable. So I'm going to sketch the region of integration. So we're given our volume integral. So we have y equal from 0 to 4 minus z. So if we have 0 to 4 minus z, then we know that I'm going to have so this is y equal 4 minus z. So I know I'm going to have an equation y plus z equals 4. So that just generally looks like this. It's a straight line. So this is y equals 4 minus z. So I'm just looking at when x equals 0 right now. So I know this is going to be one of my planes. And my next one, I have z equal to 4 minus x squared. So I'll make this green. So if it's z equals 4 minus x squared, I'm going to start off at this point here for z, because if I made x equals 0, z would equal 4. So I know I would have to have this before, because looking back at 4 minus z, so we'll look back at 4 minus z. So these points, I know x is going to be 0. So if y equals 0, that means z would have to be 4. So that's this point here. And then if z equals 0 and x equals 0, then this point would have to be 0, 4, 0. So now, going back to the z equals 4 minus x squared, so it's going to be a negative parabola, only half parabola, because again, we're only dealing in the first octant here. Here, I'll make this blue line a little bit less exaggerated, because it's not exactly that. There we go. Oops. This is now the blue point. Alright. So that now this line right here is z equal to 4 minus x squared. So again, I know these because I'm looking at just in the plane of what the function is in. And I'm trying to imagine what it looks like from just in that plane. So I'm looking at the yz function, I'm looking at whenever x equals 0, so the zy plane. Whenever I have the zx function, I'm looking at whenever y equals 0, I'm looking at just the zx function. But now these two are going to have to protrude perpendicularly. So I know that there's going to be some boundary line. I'm not going to say what it is yet because I don't know what it is. There's some boundary line, and I know what it's going to look like, but I'm just going to draw it right here. There's some boundary line that divides these two, and you can go ahead and solve for it now if you wanted. You can solve for it whenever you want. All it takes is to make a substitution, and so you're in terms of y and x. So again, these are going to protrude perpendicularly out to that boundary line, because these are what you might call cylinders or surfaces. Because you want perpendicular. Alright, so now we have our shape. Now I can start doing the YZ projection and solving for the volume integral. So for the YZ projection, I did that in blue. It's our equation is going to look like that, because we have y plus z equals 4. Or we can then solve for, we're going to have to solve for this in terms of y anyway, so y equals 4 minus z. And then again, this point right here is 0, 4, 0. This point here is 0, 0, 4. Now when we do this volume integral, we're going to start off with x. So when we come off with x, we're going to go from negative x to positive x. So we enter out the at x equals 0, that plane, because again we're in the first octant, so we enter out that zy plane, so x equals 0. And then we exit out that green plane, which is z equals 4 minus x squared. So it's going to be the square root of 4 minus z, because again I have to solve for this in terms of x, so this becomes x squared equals negative x squared equals z minus 4, multiplied by negative, take the square root, so then I get x equals 4 minus z, square root of that. And now I need to get y, so I'll take my arrow the y direction. Oh, I thought that was black. So I enter back at y equals 0, which is the zx plane. So y equals to 0, and I come out of the blue plane, which is that 4 minus z, y equals 4 minus z. So I have 4 minus z here. And then lastly I need to do z, which again, for the last one, you should be no variables in it. So you go from the bottom to the top. So we've already hit both of these planes, so we don't need to worry about what those planes are, the equations of those planes are. We only need to go from minimum point to maximum point, which is then z equals 0 to z equals 4. So that's our volume equation. This is all one triple integral. But next we're going to have to, since we're going for dz first, so when we come up, again, we can hit either this blue plane here, or we can hit this green plane here. So now we need to find out what that boundary line is. So that boundary line is going to be, I want to set these z's right here equal to each other. So I have y equals 4 minus 4 minus x squared. So then this becomes y equals x squared. So that's our equation. So this is what it's going to look like. It's just, you know, it's part of a parabola. And then from the y plane we have the blue plane projection. From the y-axis we have the blue plane projecting. So this is the y equals 4 minus z plane. This right here is y equals x squared. And then from the x-axis, the green plane is perpendicular, protruding perpendicular to it. And this is the z equals 4 minus x squared. That's what that plane is. So now when we come up with the dz, we can either hit the green plane or the blue plane. So we're going to have to break this up into green plane and blue plane. So I'm going to do green plane first. So we do dz. We're going to come in at, we're always going to come in at z equals 0. And we're going to come out at that green plane, which is z equals 4 minus x squared. And then, or I'll do them simultaneously. Because when I do the blue plane, we're going to come in again at z equals 0. We're always coming in at z equals 0. When we come out, we're coming out of this blue plane here. So we're coming out here, or here, however way you want to look at it, either the 3D or the 2D projection, which is 4 minus z. Now we need to look at dy. So dy, we shoot an arrow in that direction. So when we look at the green plane, we enter at we enter at y equals 0 first, which is right here. We enter at y equals 0 first, and then we exit out y equals x squared. Because again, we're only looking at what happens in this green region. We're pretending like that blue region doesn't exist right now. So we enter at y equals 0 and exit out y equals x squared. And now for the blue region, when we go for that y, we're coming in instead at the boundary line, not exiting at the boundary line. So we're coming in at the boundary line, which is y equals x squared, and exit out this line here, which is, I believe, y equals 4, because we're treating this as z equals 0, so this equation right here is y equals 4. So we exit out at y equals 4. And now for dx is just going to be from 0 to 2, I believe, 0 to 2, because that is this point. So we look at this point here, this is 2 comma 0, 2 comma 0 comma 0, because if we plug in z equals 0, we're going to get x equals to square root of 4, which is 2. And then same thing will be for the other equation. We'll have x equals 0 to x equals 2. All right. So you're probably going to have a problem exactly like this. No actual solving, just setting up. Good luck on your test. I hope this helps.